as I said, all the sessions will be here, right? Normally that gate, so that door is the one to enter because, it's better not to interrupt us through this door. And the coffee breaks would be in the last, at the end of this corridor to the right? It's a white room, they call it. And all of you have the program that we have on the website. The cocktail tonight will also be there. Some of you have brought your wives, husbands, partners, whatever. We're happy to have them here at the cocktail later on, so you can tell them or send them an SMS or whatever that they're invited to be with us later at the cocktail. And you'll all have this piece of paper with 3 tickets for lunch. Right. We're going to have lunch here in the same building, in the cafeteria. Some of you already know where the cafeteria is. So please keep those tickets with you because we'll have to give them on site every day, right? That's Thursday, Friday, and Saturday. And there's one last thing, which is the dinner on Saturday evening, the kind of farewell dinner, that we're going to have in an amazing place. I mean, I said recently that San Sebastian, such a small place, has a high density of physicists, but it has possibly the highest density in the world of Michelin stars. That is, good food around here. So we're going to go to one of these very traditional, I'll tell you more the last day, one of these gastronomical societies, which is a place where they basically worship food, right? If you haven't been asked by the guy giving you the papers whether you're staying or not, please let him know because we need to know the final numbers for sure. Right. So lunches, dinner, whatever. Some of you already asked and you've seen that all over the house, except in this room, there's the login password and username to get into the network of the Wi-Fi. So I say it's all over the house, so in every wall you'll see it except in this room. But anyway, you have to get into you can try first EduRoam, all of you who have EduRoam, but it seldom works. Well, it does work for Shaul, so it works for Shaul. And then if it doesn't, then you get to the HAU guest net, and then the username and password, it's somewhere there on the walls of the building. I don't have it with me. And one last thing, we're among colleagues, students of physics. Most of us know each other. As you can see in the program, I haven't put who is going to chair which session. So if anyone wants to chair a session from now until Saturday evening, please let me know. Otherwise, you'll be allocated to one session randomly by me. Okay? Yep. Any questions, housekeeping issues? If any of you has a need for, all of you registered through this Cursos de Verano thing, and I guess that all of you have already a bill from your registration, those of you had to pay. If not, please let me know and I'll tell the secretaries here and they can do that before Friday, because on Saturday they're not here working, right? So any complaints, any things you need from the organizing system, please do so by Friday. And I think that's about it. Are there any questions, queries, problems, whatever? So 3 minutes, 2 minutes, 1 minute. Well, I'm sitting down here, but if you want to chair it, I'm happy. Okay, you chair the next one, Alex. Right, so yeah, we'll kick off with the first session. Okay, how is the dynamics going to work? I guess we all know, but we have these very long slots of 45 minutes, which means that you can talk as much as you want up to 45 minutes, but we didn't come all the way from Japan, Brazil, Minnesota, or whatever, just to talk and goodbye, right? So the advice is 25 minutes talk, 20 minutes discussion, 30 minutes talk, whatever you want to do. But let's be clear, we have a lot of time, but I'm not going to be flexible in extending time beyond those 45 minutes because you've seen it, there's lots of papers in the program until Saturday evening, right? So I'll invite Clayton and Blai and Enrique. They're in the first slot, right? So, well, I guess you can, you want the microphone and, yeah, okay.
Okay, so take your time.
So, Clayton from St. John's University and a usual member of these meetings, right? I remember, I have a few pictures of you in where was that? In Phoenix, HSS 2009, that was, in Arizona, where we had this first session on the textbooks things, which ended up, thankfully, into a book recently. So Clayton is one of the usual members of this community, and he's now retired as a professor at the university. And he's going to talk us about, that's the title? Yeah, James Franck, the ionization potentials of helium and the experimental discovery of metastable states. The floor is yours.
Okay, well, thank you very much. And thank you for organizing this thing. You must put in a lot of time. So I am going to be talking about Franck and ionization potentials as such. I should mention initially Henry Small's PhD thesis from some years back, which is really an essential resource for this material. So I'm going to begin by reminding you about some of the features of helium. It has two separate spectral series, one of which are singlets, the other of which are, well, now triplets. In 1920, they were doublets. They're very narrowly spaced. There are no optical transitions between the two series. Now this, the triplet S state, is the metastable state, and there are no, as Franck found, no optical transitions around from the ground, from this state to the ground state. Now, today, textbooks sometimes, not always, talk about metastable states, but almost always in a theoretical context. You hear about selection rules and transition probabilities and such things. But at this time, such theories were in their infancy. Franck, together with Paul Knipping and Fritz Reiche, discovered metastable states experimentally in the course of their work in ionization energies. So, a little bit of terminology. I will use modern spectroscopic notation. And just to remind you, the first number here is the term number or the principal quantum number. This superscript is the multiplicity, and the capital letter here is both the term type, sharp, principal, diffuse, and so on, and also the azimuthal or angular momentum quantum number. Finally, I briefly remind you about the principal series, as the spectroscopists call it. These series end on an S state, generally the ground state, and since it ends on the ground state, it is the only series seen in absorption. Therefore, it allows calculations of a series limit, and that series limit is in the Bohr picture, but not earlier, also the ionization energy. So the story does start with the Franck-Hertz collaboration. In 1911, their aim was to investigate John Townsend's theory of ionization by collision. And initially, as you see Hertz here saying, it had little or nothing to do with quantum theory. I'm going to have very little time to talk about the Franck-Hertz experiment, so I will throw modesty to the winds, mention a paper I published last year on them, and move right along. So in 1911, when Franck and Hertz started, not a great deal was known about helium. The situation was not much better in 1919 when Sommerfeld started the section in his Atembau with a very discouraging quotation from Faust. At that point, no lines, keep hitting the wrong button, no lines had been seen in absorption. So where was the ground state? Which series, if either one, did it belong to? The transitions to the ground state were presumed to be in the far ultraviolet, and Theodore Lyman eventually found them spectroscopically, but not until the early 20s. And I remind you again, before Bohr, these terms were not energy levels. They were simply spectroscopic terms empirically discovered by the spectroscopists. So, in 1913, Franck and Gustav Hertz used collisions of slow electrons with gas atoms to measure, unsuccessfully as it turned out, the ionization energy of helium. And in 1919 and 20, he and his collaborators at Haber's Kaiser Wilhelm Institute for Physical Chemistry in Berlin returned to this theme, and there were others that did so as well. So, I will say a little about their work on ionization potentials. Here they are in 1913. Their experiment adopted a design from Philip Lenard, who had tried to measure ionization potentials by directly detecting positive ions. And it worked like so. You had a hot filament giving off electrons. You had a mesh electrode up here that accelerated those electrons. And then in this space, the electrons bumped into gas atoms. Now up here, the collecting electrode was biased so that it would repel all electrons but attract positive ions. So when you see a sharp uptick on the electrometer, you say, aha, positive ions. And you see them finding what they thought was the ionization energy at 20.5 volts. Now, in fact, they weren't seeing ions at all. In modern terminology, the idea was that they were knocking an atom up into an excited state. It decayed, giving off ultraviolet light. That ultraviolet light led to photoelectrons being emitted from the collecting electrode, and, you know, electrons leaving, ions arriving, same thing. They returned to this theme in 1914 in an experiment primarily designed to measure the ionization energy of mercury. They found that their 1913 method did not work. So instead, they adopted a scheme related to their method that they've developed for measuring energy loss in collisions. So the peaks, here's the mercury picture, which is, I expect, fairly familiar to a lot of you. The peaks represent the onset of inelastic collisions, but they also repeated this version of the experiment for helium, and once again found the same value, 20.5 volts, which they took to be an encouraging sign. Although, as it turned out, just as in 1913, they were not seeing ionization. They were seeing photoelectrons. Well, in August, this was in April, in August they found themselves in the German army and did not resume experimental work until after the war. But their experiments excited a great deal of interest and emulation, mostly in North America. I will mention only the culminating experiment by Bergen Davis and Friedrich Gaucher at Columbia University in 1917. Gaucher appears to have been camera shy, but he was the one who devised a very clever technique. I've superimposed it on the Franck Hertz apparatus picture. He introduced a new electrode, very close to the collector, and by biasing that electrode appropriately, you could distinguish between photoelectrons and positive ions. It was really a very clever technique. And the results were unambiguous. They found that Franck and Hertz had been seeing photoelectrons and not positive ions. Well, in 1919, in their last joint paper, Franck and Hertz returned to the fray in an article published barely 2 months after the armistice. It was a long review article. They showed that somehow or other they had learned of the North American work and realized that in both mercury and helium, they had been seeing excited states and not ionization potentials. And in addition, they had become enthusiastic proponents of Bohr's theory, which they had not so much as mentioned in 1914. Now, just an aside here, I won't have time to say much about it. The possibility of ionization by multiple collisions with quite low electron energies did come up during this work that was done in North America during the war, and was probably one of the things that did raise in Franck's mind the possibility of metastable states. That story, though, goes beyond what I'll have time to talk about. So, we come back to helium, which in 1919 was still not terribly well understood. I'll be talking primarily about 3 papers. One by Franck and Paul Knipping that measured ionization potentials. It was also mentioned by a group in Britain and by Carl Compton in the United States. And again, I will not have time to say much about that work, some of which was very interesting. Then in the following year, 2 more papers. Franck and Fritz Reiche made an argument for metastable states, and Franck and Knipping did a second experimental paper in which likewise the possibility of metastable states emerged. There are 2 contexts here. The one is Lande's 1919 model of the helium atom. And the second one, which I think is probably not as well known, in 1914, Friedrich Paschen did manage to see in a very innovative experiment 2 lines of helium in absorption. And so I'll be saying a little bit about that as well. So first, the theoretical context, Alfred Lande's model of the helium atom. It built on what Sommerfeld called his double star model and envisions one electron fairly close to the nucleus and another one farther out. In Lande's version, the orbits are inclined at a roughly 90 degrees for the singlet series. You hear talk about crossed orbits, but are coplanar for doublet states. And you notice here, this is something Franck made a lot of. You notice that in some sense this picture is similar to a hydrogen atom. You have one electron, or an alkali. One atom is farther out from whatever's going on around the nucleus. So what is this resonance fluorescence all about? The phenomenon was discovered in 1904 by the American spectroscopist Robert Wood. It's a very pretty experiment. There's one on YouTube, I think. What he did, he illuminated sodium vapor with a beam of light from the bright yellow D lines of sodium. The vapor absorbs that light and re-radiates it in all directions with light of the same wavelength. You see his picture here, which I'll let you read. Again, this was long before Bohr and company. He saw a few years later the same phenomenon for this line in mercury, which had also been seen by Franck and Hertz in 1914. So what's going on? In modern terms, this is a term diagram for potassium, but it's much the same as for sodium. The idea here is that once you kick an electron up to one of these states, it has nowhere else to go but back to the ground state. So all the light that is absorbed is re-radiated at the same frequency. And just, again, an aside, in 1914, both Paschen and Franck and Hertz interpreted these resonance lines as atomic electrons behaving like quantized Planck oscillators. There was no mention whatever of Bohr and his new theory, which had been out for about a year. So, what was Paschen's experiment? Unfortunately, it is a beautiful experiment, and I don't have time to describe it in detail, but you can see what Wood said about it. One of the most remarkable ever performed in this area. So, remember I've said that in 1914, no absorption lines had ever been seen in helium, although these two infrared lines at about, 10,800 and 20,600 angstroms had been seen in emission. Paschen ran a weak current through a discharge tube containing very pure helium. He describes a purification process that took him 6 months, if you can believe it. And under these circumstances, with this current, with this tube with a weak current running through it, he was able to see these lines in absorption. Moreover, he found that the line in the triplet series was a resonance line. All of the radiation that went up to that state came right back down here, but the corresponding line in the singlet series did not show resonance. So, on to Franck and his associates. This is the first paper that Franck did with Paul Knipping. I hope I'm saying that at least approximately correctly. He had studied with Röntgen in Munich, and in 1912 he was one of the group that had confirmed Lowey's predictions of X-rays. In 1919 he was working with Franck at Haber's Institute. Their apparatus returned to the one they had been using in 1913. They had discovered apparently the problems that they'd run into earlier. Lenard's method for direct detection of positive ions with this extra mesh electrode to distinguish ions from photoelectrons. And in fact, they came up with 3 methods to measure the ionization energy. Apparently, having fouled it up once, Franck was taking no chances. So the first method, notice that if you start from this 2 level, helium has 2 principal series of sorts, not from the ground state, that go up from this n equals 2 level. The series limits were known, and you see them here. So they measured the first excited state, which they took to be this lowest lying line in the triplet series. That was, remember, 20.5 volts. Confirmed they were seeing photoelectrons, defined the ionization energy. They simply added this 4.8 volts to their 20.5 volts and found a little over, to his 20.5 volts, and found an ionization energy of a little over 25 volts, compared to the theoretical predictions, which were around 30 volts. They also saw just a hint of this second term being excited, about 0.8 of a volt higher in the singlet series. Their second method, I'll mention overly briefly. They looked through the whole range. They found, again, directly, this ionization energy at 25.5 volts again, and found that indeed it showed, what's happened to my pointer? Well, they found that it showed no signs of photoelectrons. The third method, they measured the ionization potential for the removal of both electrons and found this value of 79.5 volts. Now, the ionization of singly ionized helium was well known, both spectroscopically as the term series limit, and theoretically. Singly ionized helium is just a hydrogen atom with a helium nucleus, so it was known to be this number, 54 volts. So you subtract the one from the other, and once again, get about 25.5 volts for the ionization energy. And by this time, they seem pretty sure of themselves. In this 1919 paper, they made only a brief mention of metastable states, but it's clear the idea was in the back of their minds. They make a reference to Paschen's resonance line here, the one in the triplet series, and then in a brief footnote, they say, this point appears to us to suggest that the alkali similar state, note the allusion to Lande's theory, is, so to speak, metastable. And then that theme was continued the following year when Franck, Knipping, and Fritz Reicke developed a two-pronged attack in that direction. So first, an overview. Franck and Reicke used Paschen's experiment to argue that this triplet S state is metastable, and the ground state had to be down here with the singlet series. Franck and Knipping found first that the 20.5 volt level in the triplet series appeared only in impure helium, and argued that as a result that state was metastable. They also found something I'd seen only a hint of earlier, that the they found this singlet S state at about 21.2 volts, about 0.8 of a volt higher. Now, something that I found really fascinating, both of these papers used arguments that were entirely experimental. Nevertheless, they both emphasized Lande's picture of the helium atom. They really wanted a physical picture, and the way they used it, as we'll see a little later, at least suggests to me that tells us something perhaps about the state of quantum theory at about this time. So first, Franck and Reicke. Reicke was a student. He was later an assistant of Planck. He was very much part of the Berlin circle of physicists in which Franck moved, and at this time, he was a theoretical advisor at Haber's Institute for Physical Chemistry, where Franck also was. And you see this summary of their conclusion from the evidence that this line in the triplet series is a resonance line. One can conclude with certainty that in normal, that is ground state helium, only the cross state is present. In more detail, they pointed out there, again, as we've seen, there are no transitions between the singlet and what they took to be doublet series. They knew that Paschen's experiment saw absorption of both of these lines, one at 10,000 and the other at 20,000 angstroms, but that the 10,000 line showed resonance, so that this triplet P state could only go back to the triplet S state. It had nowhere else to go. By contrast, the line over here, this 20,000 angstrom line, did not show resonance, suggesting that, all right, that an electron up here could either go back to the 2 singlet S state or down here to a 1 singlet S state, which therefore must be part of the singlet series. And they even had an early version of one of these term diagrams. I'm being just a little anachronistic in including them here, which again, I won't take the time to talk about in detail. So that was Franck and Reiche. Here is Franck and Knipping's 1920 paper on the excitation potentials of helium. They had improved their apparatus. They had also developed their techniques for purifying helium. And their aim in the experiment was both to confirm the hint they had seen of this singlet S state and to see if they could find more evidence for the metastability of the triplet S state. And they found remarkably that in very pure helium, this 20.5 volt energy of the triplet S state disappears. They didn't see it. How did they know? You have uncertainties in initial electron velocities, so they said the way to measure the excitation potential most accurately is to measure the voltage distance from the ionization potential at about 25.5 volts. Well, their kink, as they called these things in their graph, was 4 volts lower. Just that 4 volts right there. Whoops, sorry. Just the 4 volts right up here. And so, without question, they were seeing the singlet S state, the triplet S state at 20.5 volts, half a volt lower, simply did not appear even though it must have been excited. It had to have been. So the conclusion is that an electron kicked up here could not decay, at least could not decay optically to the ground state and was therefore metastable. So the next stage was to repeat the experiment for less pure helium. Essentially, they let their cold trap boil down a little bit so that they got some impurities in their tube. And lo and behold, the 20.5 volt state is back. And here is their picture compared to their earlier one. Here's the ionization potential. 4 volts below is still the singlet S state. And down here is the 20.5 volt state that had not appeared. So what was going on? Now the first part is experimental, but the rest starts to show us the influence theory was having on them. In pure helium, the idea is the electron just sits in that triplet S state. It does not undergo an optical transition to the ground state. For less pure helium, they noted that helium in the excited coplanar state, the triplet state, remember, is chemically very similar to a lithium or hydrogen atom, and in collisions with impurity atoms, helium and impurities can form short-lived compounds which decay with the emission of ultraviolet light. In the process, helium returns to the ground state without itself radiating. And again, here is this Landes picture that suggests this lithium or hydrogen-like behavior. It's not altogether wrong, but the situation, that picture did not hold up in detail. And in his 1926 book on electron collisions, Franck more or less abandoned the idea and just talked much more generally about collisions with impurity atoms. Now, continuing with the role of theory, notice again in both papers, the arguments for metastable states are entirely experimental. Paschen's experiment on the one hand, Franck and Knipping's experiments on the other. Nevertheless, they were all three impressed with and relied on Landes' picture. They speak consistently of crossed orbits and coplanar orbits instead of singlet and doublet states. I'm going back and forth between doublet and triplet here. I hope that's not too confusing. And notice how enthusiastically they are talking about Lande's theory. Lande has carried out the spatial quantization only provisionally, and a new exact calculation is expected. However, absolutely no ground exists to doubt the correctness of the chief conclusions. And even going beyond this sort of thing, they bring up selection rules in a way that I found puzzling. I know some of you are working on selection rules. If you have any thoughts along these lines, I'd be happy to hear them. So anyway, here are Franck and Reiche in 1920 talking about selection rules. They first point out here that from the absence of combinations of the two systems, we further conclude that a transition from a higher orbit of one system to a lower of the other never takes place by monochromatic radiation. These facts describe a very impressive confirmation of the selection rules of Bohr, Rabinowitz, and Sommerfeld, which leads to the conclusion that for radiation, the invariable plane of the atom remains fixed. So the invariable plane, by which they meant the direction of the atomic angular momentum, is a clue that they were relying primarily on the Rabinowitz-Sommerfeld version. If K is the azimuthal quantum number, and I've pointed out the relation of that quantum number here to the terms, for Rabinowitz and Sommerfeld, delta K could be 0 or plus or minus 1. For Bohr, just plus or minus 1. In either case, there appears to be no such selection rule that tells one anything about transitions between the two spectral series. This was really puzzling. I've put in a speculation down here, but I've put it in very light print because I don't really believe it. But it's not clear just exactly what they were talking about. I can imagine Franck getting himself confused on theory, but Reiche was a first-rate theorist. So anyway, the theme came up again in a paper by Franck and Erich Einsporn in 1920, returning once again to Mercury. And notice from this graph just how good Franck had become in designing experiments that let him pick out the various excited states. And in a bit of bragging out down here, they say, we would like to point out that the conclusions of Bohr's theory can be confirmed with great rigor, and that this experiment appears to us to describe a useful supplement to spectroscopic methods. But now their use of selection rules in connection with metastable states, which to me sounds even more peculiar. So here we are with the term series of Mercury. Like helium, Mercury has a triplet series and a singlet series. The three lowest lying p states are well separated in energy in Mercury. And notice, by the way, there are, unlike helium, there are intercombination lines between the two series. Now, one of these p states, the one circled in red here, that's the prominent resonance line that had been found by Wood around 1907 and seen by Franck and Hertz in 1914. The other two do not show optical transitions to the ground state, even though Franck and Einsporn did see kinks in their current voltage graphs showing that those two states had been excited. And here they are describing it. The selection rule could give us a possible answer. And now, again, a passage that seems to me even stranger. If one considers radial, azimuthal, and spatial quantization, then from the selection rule, an electron which can be raised to a higher quantum orbit by an electron collision cannot, in all cases, fall back into the rest state by monochromatic emission. On the contrary, the occurrence of metastable states in analogy to the behavior of helium is exceedingly probable. And again, the argument for metastable states is again pretty much an experimental one, the use of selection rules really struck me as hard to understand. I'm going to, and they weren't the only ones who were doing this sort of thing. Here is Walter Gerlach in 1921 in a book that, on the experimental foundations of quantum theory, and he bought into the whole picture. That both helium and perihelium, that is both the singlet and triplets, have entirely separated series, is the realization of the requirement that electron jumps from across into a coplanar state or inversely may not take place from the selection rule, Sommerfeld, Rubinowitz, and Bohr, and then ducking the matter very nicely, which we cannot go into here. A marvelous line, I thought. And then goes on, the two-quantum coplanar helium thus shows a metastable form to which a type of alkali is to be attributed, but then coplanar helium must also have electron affinity and with it chemical activity. I think I will skip over the next slide, which is another example of the same thing, and conclude here. I've repeated Sommerfeld's quoting of Faust and adding Mephistopheles' rejoinder some lines later. And perhaps the question for historians is if Sommerfeld rather is Faust, to whom do we assign the role of the devil here? Well, this is an interesting question. In any case, Franck and Knipping had found the ionization potential of helium along with Horton and Davies in Britain and Compton in the US. The Horton and Davies experiments are particularly interesting, and I wish I had time to talk about them. Franck and company had also argued persuasively for the existence of metastable states. That argument was entirely experimental and would have been unchanged if they had spoken only of singlet and doublet spectral series. Nevertheless, they badly wanted a physical picture, and so consistently used Lande's crossed and coplanar orbits, and even appealed to selection rules that, as far as I can see, didn't quite exist. It's an interesting story that, again, may tell us a little about quantum theory around 1920. And that's it. Thank you.
So I'm here chairing, and we have just 10 minutes for questions, comments, and sorry, I have one of these clips here.
Is that working? Yeah. I just didn't quite understand your point about the selection rules. I mean, one could, of course, say, you know, whenever there is a transition missing we're expecting there must be a selection rule.
Well, that's, I think, essentially what they were saying. But the problem is there wasn't one in 1920. There was no selection rule that said anything whatever about transitions from triplet to singlet states in helium. Mm-hmm. And there were... Now, as I've said there in gray, they may have thought, this is a speculation that I don't... Yeah.
Yeah, now I get it.
Yeah.
Well, there's an ambiguity there what the which refers to. Does it refer to the confirmation or to the selection rules?
Yeah, and I think that ambiguity is in the German. I'd have to look back. But no, I think they are talking about the selection rules.
Yeah, Arianna, I think. I'm gonna just.
Yes. Again, to the directly to the selection rule, because as as far as I remember from my work, I never looked at these papers. At this stage, you have from the theory the proposal to explain some missing lines. You know that there are some
Sure,
lines, yeah?
sure.
And you have Bohr's derivation, and you have the Rubinowitz-Sommerfeld,
Right,
who
right.
appeal to this conservation of angular momentum.
Right.
And the problem is that at that stage, you don't really know these quantum numbers.
Yep.
For example, even what physical thing they mean. And for example, in Rubinowitz, you have first, he says that this azimuthal represents the angular momentum, but then there are other, there are all these shifts. I don't know where this picture comes from, where how Franck and Reiche, how they label their levels. Because people start using some strange quantum numbers to label their levels in these cases where you don't really have a theory. And so the problem is a little bit, I don't know in this case, they say, oh yes, we are clearly missing.
Oh, sure, that's how it started.
Yeah.
And in fact, a few months after these experiments, Sommerfeld introduced his internal quantum numbers, which Franck and company did not know about, but which wouldn't have helped.
Yeah, but we know it wouldn't have helped, but they didn't, they were just trying to give some physical interpretation to these schemes that they were working out.
That's apparently what they were trying to do.
So I would not say that there was no selection.
Well, there wasn't anything that explained the phenomenon they were talking about.
Well, they were
That is, these selection rules work just fine if you're trying to explain, say, in just one of these series why some lines are there and aren't in others. But they say absolutely nothing about the triplet-singlet transitions.
okay.
It may well be, yes.
It's even worse. These the missing transitions between the singlet and the triplet lines should be there on accordance of the selection rule, right?
Yeah.
That's
One thing is it's clear, and in fact, one of the things that comes out to me from this stuff, there was a great deal about helium that was not understood in 1920.
Okay.
And one can really be led astray, I think, by concentrating too much on attempts to calculate energy levels and ground states and all that. Those are important, but there was a great deal more that people did not understand.
My question would be, like Ariana's, which kind of representation did they use exactly for their spectroscopic classifications, apart from whether they used the Landé spatial...
They didn't talk in terms of theory much at all.
No, but which kind of representation did they use
How do you mean?
term schemes? I mean, you said that this is a modern scheme and you...
No, I'm saying the notation is modern. At this time, there were several competing notations.
But
I think they used Passion's version.
Are these
But
diagrams taken from the...
no,
Franck and-
no, the diagrams are modern. They started to be introduced about 1920, so they aren't completely anachronistic. But the terms were already very well known. They're in Dunz's Handbook of Spectroscopy. Dunz was a student of Passion. They were well known to spectroscopists. So the diagrams came a little later. But the understanding of the terms and the term series themselves, that was very well understood. That was spectroscopy that the spectroscopists had been working on and pretty much finished up by early in the century.
These diagrams are a very important and very powerful tool then later on, of course.
They help you visualize it, and it's why I use them here. Today we're familiar with them. But again, it's apparent from reading these guys, they really understood, they really had these diagrams of this sort in mind. They knew what the spectral terms were, and they knew what spectral lines were present, and which ones that should have shown up just by what's his name's term difference scheme, which one should have shown up, and not all of them did. And that, of course, is what the selection rules were trying to uncover.
I think Tony has something to add to that.
Yeah.
Comment on a brief question. Yeah, I don't need that. I'm pretty loud. Of course, at the same
was to introduce
Sure.
precisely to introduce the inner quantum number, to have an additional selection rule to explain the absence of transition, which would otherwise be perfectly impossible.
Exactly so.
On the basis of more Sommerfeld-Rabinowitz, right? So that's happening at the same time that Sommerfeld had, and is about to in a year introduce inner quantum numbers.
Even the inner
to
quantum
do
number
that.
does not help.
No, I'm not talking about an optical spectrum, not the helium spectrum, where there is a separate issue. But what I didn't understand exactly, since I haven't studied the Landé picture, is why are the coplanar orbits supposed to be a triple?
That distinction was made empirically. He tried to calculate energy levels and got better agreement with the crossed orbits and the singlets and the coplanar orbits and the triplets.
States by having coplanar orbits. You have a triplet.
But they were doublets in 1920, and he didn't try to explain even the doublets. They are, yeah, but they were only doublets in 1920, and he made no. I don't think he made much attempt to try to explain them.
Experimentally resolved.
Yeah, exactly. That experiment came right after Heisenberg's helium paper in 26.
And the doublets were, why would there be two states that have coplanar orbits?
That was not addressed. There were some states, I think it was in one of Bohr's theories, that splitting, now in Bohr's theory, both electrons were in a low one quantum orbit. And in one case they were going the same way, and in the other case opposite directions. They tried to explain the splitting there, but it was much too large. It didn't work at all.
Which is close to what, a year later in the core model, or a year and a half later, right?
Yeah.
That's how the doublet structure in optical spectrum would be explained in the Rumpf model.
Yeah, yeah.
The varying orientations of the angular momentum of the core relative to the
Right,
difference.
right.
So I was just wondering if Andy had done the same thing.
As far as I know, he did not. It was just empirical. He tried to calculate energy levels. The results weren't very good, but he found better agreement between the crossed orbits and the singlets, and correspondingly.
Okay, it's my role to have selection rules, so we have two last questions, Gyura and Alex.
A question just in a different direction.
Yes.
Do you have an explanation why the conversion of Franck and Hertz came so late to the Bohrian?
Well, that's an interesting question, actually, and a very puzzling one. Their 1914 papers came out about a year afterwards, and their memories, it turned out, are misleading. In 2 interviews, Franck said very emphatically that they didn't know about it in Berlin, nobody talked about it, nobody mentioned it, completely unknown. But then, about 2 months after the second interview with Thomas Kuhn, Franck wrote Kuhn a letter and said, you know, I've just looked back at my Nobel lecture, and it looks from that as though maybe we did know about it. The passage to me reads as ambiguous. What he did not do was look back at his 1926 book with Jordan, which says very flatly that in 1914 he and Hertz didn't know about the Bohr theory. And just to make it more confusing, 63 or 64, he wrote an obituary for Bohr in which he said they actually thought about the Bohr's theory but found reasons to reject it. Hertz was more consistent. He wrote an account in the 60s and elaborated it later, but always said much the same thing, in which he said, well, the Bohr theory was certainly known, it was certainly talked about and discussed energetically in Berlin, and that seems to be the case. Helge Krag's book has a lot of examples of it. And then he says, sounding a little puzzled, but at that time he said the emphasis was primarily on the hydrogen atom, and perhaps for that reason they hadn't thought to apply it to their experiments. So the best guess is, you know, I don't want to dismiss too lightly Franck's statement in 1926 that they'd never heard of the thing, but the best guess is that they knew about it, had perhaps not thought about it too much. They were experimentalists and working hard on the gadgetry, and perhaps had not seen, or for other reasons had rejected the thought of applying it to their work.
Alex, just to finish.
Yeah, just a very on rereading the sentence, it doesn't seem to be ambiguous actually, because the leads being in a singular clearly means that this refers to the confirmation, so that the experiment actually shows the appearance of a new selection rule rather than the selection rules implying this beforehand that the invariable plane remains fixed.
I wouldn't read it that way. I wouldn't read it that way. I mean, they say that the confirmation of the selection rules of Bohr, Rubinowitz, and Sommerfeld.
Yeah, okay, period. So
Yeah.
Basically, the selection rule is just saying there are transitions that aren't allowed. And this confirmation leads us to the conclusion that radiation, that we have here a special instance of the selection rules being that the invariable plane of the atom remains fixed. And I think if you read it that way, it's not really surprising. They just say, well, we have disallowed transitions that fits into the general scheme of
What they may have been indeed saying that there must be some sort of selection rule involved here. But if they're referring to the Bohr, Rubinowitz, and Sommerfeld selection rules specifically, that doesn't help them.
No, absolutely. But I think if one reads it as the conclusion being a conclusion from the experiment rather than a conclusion from the established theory, I think it makes absolute sense and is not really that surprising. They say we have disallowed transitions. We have a general theoretical framework for that. And I think if one, and I would like to see the sentence in German, of course, but I think as it reads, that is really the only way to read it.
Well, there is one other wild speculation, which is that if you change the word atom to radiating electron, and you say the radiating electron cannot change its invariant plane, then obviously you can't go from a situation where both electrons are rotating in the same plane to a situation where one is in this plane.
Yeah, that's...
Okay? If you say that it's the radiating electron, not the whole atom, the radiating electron.
Okay. Tony, Alex, Ariana, this is just the first paper. Wow. Thank you. Yeah, thank you all of you. Thank you very much, Clayton. And now we're moving to the next paper, which I